Thank you very much for giving me the opportunity to speak. It's been a wonderful and very stimulating workshop. So I'm going to tell you about the quantum mechanics of the Hartle-Hawking state. And this is joint work with Christian Jensen in a paper that came out this summer. And I'll tell you a little bit about some work in progress as we go along. So specifically, we're going to focus our attention on the no-boundary wave function of the universe. The context is going to be asymptotically de Sitter spacetimes. I'll choose the convention that we work in d spacetime dimensions, that is d minus 1 dimensions of space and 1 dimension of time. So this is a cartoon of the topological expansion of the no-boundary wave function in asymptotically de Sitter space. This is the contribution of leading topology in which the spatial cross-sections are spheres, and there can be other contributions as well. And the focus of our talk is going to be on the contributions coming from the leading topology, which is to say where the spheres are SD minus 1s, the spatial cross-sections are SD minus 1. So this is an object which is commonly referred to as the Hartle-Hawking state, and let me review what that means. We're going to consider a no-boundary spacetime where we have a metric gamma at asymptotic infinity. That is, we're going to expand the space, the asymptotically de Sitter spacetime in a Pfefferman-Graham expansion, and let gamma be the leading spatial metric at asymptotia on the d-1 sphere. And this gamma is defined modulo diff times Weyl. I'm going to denote the Hartle-Hawking state by HH in these double brackets. And the double brackets are going to remind us that this is a state that lives in a Hilbert space for gravity. I'll say more on that in a little bit. And the significance of this gamma is that it will provide a basis in which we are going to expand the Hartle-Hawking state. So we'll write this notationally as follows. And I'll call this inner product psi of HH of gamma. So this is nothing, at least immediately mysterious at the level of notation. If you have single particle quantum mechanics and you have a state psi, you can expand it in an x basis and get psi of x. You can think of this then as an analog of like the x basis in quantum mechanics. This is a different kind of basis. It is a basis of metrics at asymptotia in which we are expanding the Hartle-Hawking state. Our goal in this talk is going to be to compute the norm of the Hartle-Hawking state to one loop in perturbation theory and gravitational fluctuations. What this will entail is an integral over the norm squared of this quantity over asymptotic metrics modulo diff times Weyl. That is, we're going to glue together the bra and the ket at asymptotia. And we're going to see what answer we find. Now let me make a comment on what answer we might expect to find at the level of picture analysis. So if I draw the Hartle-Hawking geometry, I'll define more precisely what this is shortly. We might consider gluing the bra to the ket in this fashion. And we might imagine that the Lorentzian part here and the Lorentzian part here would cancel out and would therefore give us something like the sphere partition function. Now, this is the answer that I expected to find, and then certainly this is the answer which is true at tree level, at the level of looking at the on-shell actions. However, there's a number of confusing things about this possible answer that I want to highlight. The first is that we know that the one-loop sphere partition function, due to work of Polchinski and others, and has been discussed a number of times during this workshop, that the sphere partition function contains these factors of I to the d plus 2. These unbecoming factors of I to the d plus 2 are a problem when we want to leverage the sphere to think about the static patch entropy. But they're also a problem for this interpretation as well, because we would like the norm of a state to be something which is positive or positive semi-definite if the state is null. And this does not look like a positive number in general space-time dimensions. So this would be a puzzling answer to find indeed. The other thing I want to bring to your attention is the following, is that for general gamma, for general metrics at asymptotia, it is not the case that the corresponding spacetime that you fill in will cleanly separate into a Lorentzian component and a Euclidean component in the same manner that the Hartle-Hawking geometry does. So the Hartle-Hawking geometry, again, has this Lorentzian throat and this Euclidean cap. But for more complicated complex spacetimes, this mechanism that we might imagine in our heads of the cancellation of the Lorentzian parts and the survival of the Euclidean parts may not obtain when we have more complicated geometry. So that picture is going to be complicated by fluctuations or by the integration over gamma. So let me tell you the answer that we find, and then I'll spend the rest of the talk explaining to you how we find it and have some speculations as to what it means. The answer that we find is that at one loop, we get an answer which looks like the absolute value of the sphere partition function in terms of the order 1 coefficients. But there's a division by the volume of the de Sitter isometries, or if you prefer, the volume of the conformal killing vectors on the d-1 sphere. So this is some finite number in zeta function regularization divided by the volume of SOD1. And this is a non-compact group, which it has an infinite volume, and therefore at one loop we get that the answer would be 0. So we'll talk about what this means, but the claim is that the Hartle-Hawking state in Einstein gravity is a null state at one loop. And moreover, this persists when we couple to Bunch-Davies matter. And I'll also discuss what happens when you couple to an inflaton. That story is a little bit more subtle. So first, let me comment on the inner product on asymptotic states, which I alluded to briefly so far. We're going to consider a treatment of the inner product on asymptotic states, that is, these metrics gamma at asymptotic infinity. And there's a very nice discussion of this in this paper by Chakraborty, Godet, Paul, and Raju in 23. I recommend this paper. It has a lot of nice calculations, and in particular looks at computations of correlation functions at asymptotic infinity. But we're going to consider here something simpler than correlation functions, which is not inserting any operators at all, and just looking at the norm of the state itself. So as I said, the basic picture is that we're going to look at the norm of some state psi, where we are going to integrate over asymptotic metrics modulo diff times vial. So the picture that you should have is the following, that if I hand you a wave function which is already expanded for you or given to you in the gamma basis, I give you a wave functional psi of gamma, then in order to compute its inner product, you need to insert into it a resolution of the identity in the gamma basis. And the resolution of the identity in the gamma basis, here's the ket and the bra, is one where we integrate over all gamma modulo diff times vial, and that this comprises the resolution of the identity. This is the basic picture, which is shared by these two papers. And of course, to implement this type of integral of gamma modulo diff times vial, we have to do some Faddeev-Popov gauge fixing and be very careful. So there it is that this integral over asymptotic metrics is going to be part of a calculation where the gauge fixing and its details are going to be of utmost importance. With this in mind, let's proceed to compute the norm of the Hartle-Hawking state to one loop, at first in the context of pure Einstein gravity. So to compute the norm of the Hartle-Hawking state at one loop, we have this kind of expression. But let me expand it slightly just to draw to mind what the different objects here mean. So when we write down psi of hh of gamma norm squared, what we have in mind is that we're going to set our asymptotically de Sitter boundary conditions where we impose the asymptotic metric gamma, again at the future d-1 sphere. We're going to integrate over smooth complex geometries that terminate in this gamma that have no boundary, that have the requisite topology. And we're going to integrate this, so this is e to the I Einstein-Hilbert action plus boundary terms. And this is the full quantity that we have in mind when we say we compute the norm of the Hartle-Hawking state. Now there's a saddle point of the integral in gamma, where there's a saddle point when gamma is the round metric on the d-1 sphere. So what we're going to do ultimately is that we're going to consider this computation where we expand in fluctuations around the metric gamma naught, the round metric on the asymptotic sphere. Let me say a bit about this saddle to which the metric on the round sphere corresponds. So the bulk metric, which corresponds to the metric on the round sphere at asymptotia, is the Hartle-Hawking geometry from which the Hartle-Hawking state, is intimately related. So this is this picture that I've drawn on some previous slides and that we've seen in a number of talks before. And the picture that you should have for it is that the universe begins in some Euclidean hemisphere, which then is glued to a Lorentzian throat that expands exponentially. This is the upper half, if you will, of global de Sitter space. We can think about this metric as being a version of the global de Sitter metric, but with a complex time contour. So this is the metric of global de Sitter space. And if t was purely real, it would describe kind of like a bounce, if you will, where the universe, at least in these t coordinates, starts off large. At t equals 0, there's a bottleneck, and then it grows exponentially as t goes to infinity. What we're instead going to do is to consider it along the complex time contour, where t starts off its life at I pi over 2 and goes down to 0. So that's going to carve out this Euclidean hemisphere. And then it's going to run off to infinity along the real axis, which is going to give us this Lorentzian throat up here. So this is the Hartle-Hawking geometry, which corresponds to the leading saddle in our, we don't know if it's leading saddle, but it is the plausibly leading saddle in these fluctuations. So at least is a stable saddle. So as I said, we're going to take gamma and we're going to expand it in gamma naught plus fluctuations h, where hij are the fluctuations of the metric on the round sphere. So we're going to examine this quantity. Let me write it in my wave function notation. So psi hh of gamma naught plus root g times h. So what you get, I'll be schematic, but we'll unwrap some of the different features of this answer, is you get some one loop prefactor coming from one loop determinants. You get e to the s naught over 2, which is related to half of the de Sitter entropy. And then you get this Gaussian, which is an expansion. These L's you can think about as hyperspherical harmonics. And there's coefficients here, psi L, which we'll study in a moment. And then you have fluctuations that would come from higher loops. So let's unpack this result. In particular, let's understand some of the details of this Gaussian in the fluctuations around the metric on the round sphere. So what I've done here in the second line is we're just going to look at this term right here, just this Gaussian term. So I've rewritten it. And here's writing it in an expanded form in some nice notation. So here's what you need to know about this object. So let's focus on d, which is the total number of space-time dimensions, being even for now, so that we avoid the complication of anomalies. And what we see is that the fluctuations hij, hkl are contracted against a kernel, which I've suggestively written as the form of a stress tensor two-point function on the round sphere. So the simplest way to understand this result is that the late time de Sitter wave functions behave like CFT partition functions in d-1 dimensions coupled to sources which include a metric gamma. Now, just to point out, you could have guessed this answer at the level of symmetry analysis, or if you like, you could use your DSCFT hat to imagine that this is what the answer should be. But one can compute this directly. But I just want to point out that we should not be surprised that the hij, hkl fluctuations are integrated against a kernel which has this form. Now, there are two crucial features of this wave functional, or rather of this Gaussian, which we are going to leverage in our analysis. So let me highlight them here. The first is that there are no bosonic zero modes, and there are no wrong sign modes. This has to do with the fact that the real part of the kernel is positive definite. The other crucial feature, which again should be unsurprising, is that the wave function is SOD1 invariant. So it would make sense that if we expanded in perturbative fluctuations, that the one loop Hartle-Hawking wave functional should be invariant under SOD1. And indeed it is. This is a consequence of just staring at the form of this. Okay. So let me provide now a sketch of the computation of how you compute the norm. We can go into further details of this. So first, as I pointed out, The Hartle-Hawking state at one loop is a Gaussian over fluctuations of the metric at future infinity around the round sphere. Said that's what we're going to do. And as I said, the round sphere, gamma equals gamma naught, is a stable saddle point of the one loop norm. And when I say we're going to do a computation at one loop, I mean that we are expanding in fluctuations around this saddle in particular. Now, to integrate over fluctuations, we have to gauge fix the diff times Weyl symmetry via Fedotov-Popov. And one way that you can do this, a convenient way at one loop, is to fix the non-transverse traceless fluctuations of gamma to vanish. So you can impose a transverse traceless gauge fixing condition on the metric and its fluctuations. Now, when you do so, and you examine the ensuing path integral, what you find is that there are no bosonic zero modes. This is related to the fact that the wave functional does not have any bosonic zero modes. But there are ghost zero modes coming from the residual diff times Weyl transformations that have not been fixed. Namely, these correspond to the SOD1 conformal isometries, which are symmetries of the wave function. So let me spell that out. So you look at the transverse traceless gauge fixing conditions, and you look at the variation of the gauge fixing conditions. And the point is that the variation of the gauge fixing conditions are equal to 0 when you evaluate them on a diff and compensating Weyl transformation that correspond to a conformal killing vector. That is to say that in the transverse traceless gauge, the one loop, that the conformal killing vectors are not fixed, so that we have to deal with them separately. Now, we then do the usual procedure that you would do when you're in gauge theory or in gravity, in which we integrate over the bosonic modes. We integrate over the non-zero ghost modes. And because of the fact that the integrand is invariant under this SOD1 symmetry, we then divide by the volume of the SOD1 symmetry, which corresponds to the zero ghost modes. This is the same procedure, by the way, that you would do in computing a similar procedure for computing, for example, the sphere partition function in string theory, or even just the sphere partition function really in any context, for example, in gravity, like Polchinski's calculation. I'll say more on this in a moment. But this is just an outline of the different steps of the computation. And it very much, let me show you the answer, and I'll comment how it's similar to other computations you may know. And what you find at one loop is you find these S0 factors, you find some one loop determinant, but you find this division by the volume of SOD1. And because this SOD1 is non-compact, as I mentioned before, this volume here is infinite. And therefore, what one finds is that the norm of the Hartle-Hawking state in pure gravity is 0 at one loop. Now let's compare this answer with the sphere partition function. And in many ways, our analysis of this is indebted to the analysis of Anino, Stanoff, Law, and Son, where they have a very beautiful beautiful methodology for computing the sphere partition function in gravity, as well as with various kinds of matter fields. So let's compare the different kinds of answers that we got. So for the sphere partition function, well, we get these factors of I to the d plus 2 coming from Polchinski. We get some other S0 dependence and some one loop dependence. Can say more on this if people are interested. But here we get a division by the volume of SOD plus 1. This actually comes from exactly the same mechanism. I mean, the computations look very, very similar. But here, the volume of SOD plus 1 is related to the conformal killing vectors on the Euclidean sphere. So one thing I want to highlight about the difference between the SOD comma 1 and the SOD plus 1. So of course, the SOD plus 1 this is compact, so this is dividing by a finite number. Okay. So the SOD comma 1, one of the reasons why we have it, is a consequence of the fact that when we consider the Hartle-Hawking wave function, we are imposing that our metrics gamma are real metrics. That is to say that if we wanted to somehow try to work with, instead of doing SOD1 conformal killing vectors, if we try to analytically continue the boosts to make them complex, these complexified boosts would turn real metrics into complex metrics for general metrics. So I just want to point out that this SOD1 is, well, there's different ways of thinking about where it comes from, but it's in part related to the fact that we are imposing real metrics in the asymptotic future. Now, in 3D gravity, I mean pure 3D gravity, one can show that the calculation is actually one loop exact, namely that the norm of the Hartle-Hawking state in 2 + 1 de Sitter is 0 to all loops. Now, one of the reasons why the 2 + 1 case is more straightforward is that there is only one metric, or there's only one equivalence class of metrics, if you like, on the 2-sphere mod diff times Weyl, for which you can take the round metric on the 2-sphere to be the representative. Now, this should be reminiscent for us about the vanishing of the bosonic string partition function. And I want to point out that this analogy is not accidental. There has been some beautiful work, including by members of this audience, on making a connection between 3D de Sitter gravity and a critical string theory. I won't get into this here, but for those familiar with the computation of the bosonic string partition function, it's heavily and in fact not accidentally analogous to the computation of the 2 + 1 Hartle-Hawking inner product. There are some differences, but that's a useful picture to have in your mind. So I want to comment on now one question that would naturally arise. So I've claimed that in 3D gravity, the norm of the Hartle-Hawking state is equal to 0 to all loops. But I've only claimed that in 4 dimensions and higher, let's talk about 4 in particular, because we might be interested in that case, that it only vanishes at one loop. So what would it take to get this to vanish at all loops in perturbation theory? Let me make a quick comment on this before moving on to discuss coupling to matter and other related questions. So there's at least 2 things that you would need to happen. One is that you would need to impose a gauge fixing condition on the metrics at asymptotia, which have the feature that to all loops in perturbation theory, that the conformal killing vectors are exact 0 modes. So in other words, the transverse traceless gauge has this property that this feature is manifest at one loop, but the calculation becomes a bit reorganized in an inconvenient way when you look at higher loop fluctuations. But there is some progress in this direction. There may, in fact, be such a gauge which organizes the conformal killing vectors in a nicer way, or rather for which its relationship to the conformal killing vectors as 0 modes is more manifest. Now, the other feature that you would need is that you would need to consider the higher loop corrections to the wave function itself. So that is, we looked at the wave function at one loop in which it was a Gaussian, but there's going to be corrections to this. And the operating picture that I have in my head, although I don't know if this is true, this is a hypothesis, is that you can look at the higher loop corrections to the wave function, and you can resum them into the exponential. So the exponential becomes a sum of different kernels, which are SOD1 invariant, such that the entire object itself still is positive. The real part is positive definite, and it has no bosonic 0 modes. So you would want to check somehow that the loop calculations sort of exponentiate into the wave function and give you some corrected version of the wave function in the manner that analogous to the form that I described. But this is not something that has been done, but I just wanted to point out what one would need to do if you wanted to try to carry this further to higher loops. So let me now discuss what happens when we couple to matter. Now, adding Bunch-Davies matter does not change the form of the result. Let's just consider the simplest case where we couple to free Bunch-Davies matter, although my intuition is that this shouldn't really be affected if we couple to an interacting theory, but there's, of course, more complications. So here now, in addition to thinking about H as the fluctuations of the metric on the round sphere, we're also going to consider chi, which is going to correspond to the value, the asymptotic value of the matter field, say a scalar, for example. Now, with one loop, the Hartle-Hawking wave function, or the joint Hartle-Hawking wave function, I should say, between gravity and matter, is going to factorize into two pieces. You're going to get the one loop contribution coming from gravity, which is the term previously computed and that I've described on the previous slides. And you're also going to get the Bunch-Davies wave function of chi at one loop. Now, in general, if you look at these contributions of higher loops, especially in interacting theories, you're going to find that there's going to be terms which mix the matter and gravity degrees of freedom. That would have to be accommodated for and studied. But at least at one loop, these two terms will factorize. And the basic point is that these two wave functions, or rather their product, are still SOD1 invariant. And moreover, they have no bosonic zero modes. So really, the only thing that you need in order to not destroy this division by the volume of SOD1 is that at least at one loop, is that the one loop wave functions in question are themselves have no bosonic zero modes and are SOD1 invariant. And indeed, in this case, they persist to be so. That is to say, we can think about the norm of the Hartle-Hawking state as the one loop norm of the Hartle-Hawking state in the absence of matter times just the ordinary kind of quantum field theoretic norm of the Bunch-Davies state using the ultra-local measure. That's what it pans out to be. So this indeed is zero by the previous arguments, which then renders this quantity zero. So by the left-hand side, by here, I'm being slightly imprecise about my notation. I mean, this is now the Hartle-Hawking state coupled to matter. And now I'm parsing it out into the one-loop gravity contribution and the matter contribution. That's what this notation means. Now let me make some comments on what happens with slow roll inflation. This is a more subtle case that we don't fully understand, but I would like to make some preliminary remarks about how it interfaces with this story, since due to its apparent phenomenological relevance. So we're going to consider some usual regime of slow roll inflation. If this is not familiar to you, well, you don't have to worry about it at the moment. If it is, we won't really get into the details. But suffice to say that what happens when you couple to an inflaton, where var phi is the asymptotic value of the inflaton, is that you get a similar story that you find when you couple to Bunch-Davies matter, where there is a factorization here between the one loop Hartle-Hawking state and the one loop inflaton wave functional. Now, the one loop inflaton wave functional actually looks a lot like the Bunch-Davies wave functional, but it has an additional term which is proportional to the zero mode of the value of phi at asymptotic infinity. Now, this extra term is very pesky, and it has been what it tells us is that the inflaton wants to be as low in its potential as possible. Or rather, a better way of saying it is that we expect that it undergoes as few e-folds of inflation as possible, which would not agree with phenomenological observations. This is discussed in this recent nice review by Juan. This is some formulation of the problem. And the question I want to pose is that I want to point out that this one loop inflaton wave functional is SOD1 invariant. Now, of course, it's not really normalizable because it has Gaussian terms, but it also contains this linear term, and I don't know how to integrate over this linear term. But at least this one loop inflaton wave function does not spoil at one loop level the SOD1 invariance of the form of the wave functions. So at least in that sense, you might imagine that it wouldn't spoil the 1 over volume of SOD1. Now, something I want to point out here is that unlike in usual circumstances where one fixes the value of the inflaton, what I'm imagining here is that when we compute the norm of this state, we're integrating over all values of the inflaton in addition to the metric fluctuations. That's just to point that out. So anyway, I don't know exactly, this is again not like, this is not a normalizable object, but because so I don't exactly know how to do the integration over it, but at the very least, because it preserves this SOD1 symmetry, this 1 over volume of SOD1 is still persistent. Okay. Another thing that we can do, inspired by recent work of thinking about observers in the context of de Sitter or enclosed universes, is to couple to a world line. A useful model of a world line was given in a paper in 2023 by Whitten. And this is the action of the world line, or rather I should say an observer. And here we're going to take Q greater than or equal to 0, P to be an R, and as such the observer Hamiltonian is M plus Q. Because Q is greater than or equal to 0, this lower bounds the energy of the observer by this mass M. If you like, P is the time variable, and its non-compactness leads to a continuous uniform spectrum for Q. So what we can imagine now is coupling the Hartle-Hawking is coupling gravity to this world line. This is some leading saddle that you would get. Here, the world line is going to dip down through the Euclidean cap and then back up on the Lorentzian portion. And we can imagine gluing this to a copy of itself and performing the integration over the data at the conformal boundary, the data up here. So we do the same procedure as we did before. So let me just say what happens. So the presence of the world line is going to break the SO. Oh, good. That's not this. Is going to break the SOD1 down to SOD minus 1. Sorry. So SOD comma 1 down to SOD minus 1 cross SOD, so SO11, namely boosts along the observer's world line. And what happens is that a time translation 0 mode of the observer can cancel against this SO11 volume in the denominator. I won't have a chance to go through the details. But what you find from this cancellation is that you get an answer which is divided by a compact group, the volume of a compact group, and as such, you find that the answer actually is positive. So therefore, an observer with a lot of entropy, because we have this continuous spectrum, gives a finite inner product. Now, I don't know whether this is a red herring or not, but it's at least an observation that seems to be worth making. This suggests a connection to, well, to not only this work, but to many of the other talks in this workshop, that maybe something about the presence of observers of a certain kind is important, even for very basic features of the Hartle-Hawking state, such as its norm, although I'm not exactly sure what interpretation to give to this computation of coupling to the world line. So let me conclude with a discussion. So we've studied the quantum mechanics of the Hartle-Hawking state and the Hilbert space in which it lives and its norm. Now, the norm is 0 to 1 loop, even with field theoretic matter. And moreover, optimistically, or in my view optimistically, this may persist at higher loops. And again, for 3D pure gravity, it's 0 to all loops. So we're interested here in gravity in higher dimensions, like 4 dimensions, or gravity coupled to matter. That's the interesting case to understand at higher loops. Now this brings into question, to my mind, issues about the phenomenological relevance of the Hartle-Hawking state and what may replace it. So there's a number of options. One possible option is that we say, okay, well, if the norm, if it really makes sense that the norm of the Hartle-Hawking state is 0 to all loops, then maybe we need to consider the subleading topologies in the no boundary state, because those then would become leading. I don't know if that's what happens. Maybe there's non-perturbative effects that we can't see in perturbation theory for the norm of the Hartle-Hawking state, that is on the sphere topology, which would render it non-zero. There's a bunch of questions that one can ask along those lines, but it's at least interesting to ask from the point of view that the norm of that the Hartle-Hawking state itself has phenomenological problems, such as due to this issue with the inflaton that I described before. Of course, there are also questions about whether the analysis that I described really survives in the presence of an inflaton. There's many subtleties there as well. So there's many questions to think about. I want to give one speculation, and this is truly a speculation. So I really still thought when I set out, when Christian and I were setting out to do this project, that we would find the one loop wave function, so the one loop partition function for the sphere. And I still wonder if there is a way of getting the sphere partition function in some fashion. So one thought, which I don't know how to make these equations precise, is that instead of looking at the norm of the Hartle-Hawking state, maybe you can instead look at quantities where you don't merge a bra and a ket, but you try to glue together a ket and a ket, or a bra and a bra. Admittedly, I don't know how to do this, or what exactly that would mean, or what the right inner product is that would be compatible with various other issues. But at least at the level of a kind of cartoon equations, you might wonder if gluing together kets and kets or bras and bras might somehow give you the answer that you would expect from Polchinski's analysis or its complex conjugate. And then we would have three different answers. We'd have the norm of the Hartle-Hawking state, and we'd have these two other objects for which we would have to really make sure they make sense and provide an interpretation. And we can have our sphere and our Hartle-Hawking norm as well on more similar footing. So with that, thank you so much for your attention.
I have two questions. So the first one, so I think your analysis assumed that the saddle point is in the region where the geometry is very big, so that you can use this as this Pfefferman-Graham expansion.
Yeah.
But then you found that the saddle point in that region gave 0. But I would have naively guessed maybe there's another saddle point where the geometry is just de Sitter sized, and then actually the saddle point is the force sphere. Because when you compute the inner product, you shouldn't only sum over really big metrics, right? You should also sum over, small metrics. And maybe the true saddle point is there. I don't know.
Yeah, so indeed, as you say, that the computation presupposes that you're summing over metrics of fixed topology and asymptotia. That's right. So that's a good question. I don't know the answer, but let me maybe make one related comment. Something that you might want to do, which is trickier to do, is to try to do the computation that I described at finite time, related to what you were saying. Yeah. And doing the gauge fixing at finite time, it's actually quite subtle, and it's something that we're in the middle of, but hopefully I can report back to you sometime soon what the result of that, and maybe it will illuminate some of the issues that you described, but I don't at the moment, no.
Okay, quickly, just the other
one. A minor comment on what Daniel said. So in principle, we are not supposed to integrate overall metrics because if we think, for example, in terms of a Klein-Gordon norm, we would just integrate only over a slice in the space of metrics where we fix some normal factor.
Yeah.
I think you are just fixing it to be big. But...
Sure, that's right.
Yeah, I mean, maybe that was related to my other question, which was there are other inner products people talk about. This Klein-Gordon is one. There's also the group averaging or the BRST approaches. So how does your inner product relate to those? So there's some nice work, but so there's a few different ingredients to that question. One of them is that I believe that there should be a connection between this and the Klein-Gordon inner product. That's maybe we can get into the details of that offline, but I want to comment on group averaging. So there was a nice reinterpretation of the result in a recent paper by Held and Maxfield. So I have some extra slide on it. Maybe I'll just put it up instead of just reading it out to you. So they did some analysis in their recent paper from this year where they were contemplating also the norm of the Hartle-Hawking state. And this is just literally taken from their paper. We can discuss some of the details, but this is their reinterpretation of the result in the language of group averaging. So anyway, that just to put it out there. But I would recommend looking at their paper in particular. Yeah.
Intuitively, if you consider a component of the Hartle-Hawking state, which has 3 particles in the final state, you might think that its norm would be non-zero. What might happen naively is that the wave function for the 3 particles would be unnormalizable, and that would be precisely killed by dividing by SOD1. That would be one way to see it.
Yeah, so relatedly in this paper by Russia et al., when they consider 3-point functions, for example, the Hartle-Hawking state, there's a similar phenomenon going on where that ends up soaking up the SOD1. But the problem is that Their answer, if it's unnormalized, is proportional to e to the s naught. So you would like to, for example, I know you're maybe saying something different about like large metric fluctuations that would look like 3 points maybe, but I'm saying if you computed at least a 3-point function, it was a slightly different calculation maybe than what you're saying, you'd still want to normalize it by the norm of the Hartle-Hawking state.
Cubic vertex in the bulk.
Yeah.
It creates 3 particles in the final state.
Coming that we insert by hand or that would come from fluctuations? Yeah. Yeah, so what I... Yeah. So, so what I think happens to these contributions, which indeed show up at higher loops, is that I don't know if this is the case, but we're trying to understand this, is that these kinds of terms will exponentiate into, for example, in this case, a 3-point kernel that would show up in the exponential of the Hartle-Hawking state and would basically serve a similar role as the quadratic term. That in the same way that we would have a Gaussian in the HH fluctuations, you would also have a 3-point kernel in HHH and so on and so forth. And that these kernels would individually be SOD1 invariant. I don't know how, I'm confused about this issue at the moment, but I agree with what you're saying that one has to deal with these 3-point terms, especially when you look at the higher loop fluctuations. And I don't know the answer to that at the moment.
As the no boundary condition in the past. Have you incorporated it and computed the one loop contribution on top of it?
Euclidean black hole.
Yes. In a black hole in the sitter, it has a no boundary in its past.
I'm not sure precisely. Well, I'm considering here. Well, okay, so the metrics that I'm considering here are asymptotically Lorentzian. I mean, maybe I just don't know exactly what you're referring to.
See on geometry to the future. Just like you connect the semisphere to the length.
Yeah. Well, anyway, the only thing I've done here is just a sum over what I believe to be the dominant saddle.
One way to interpret this question
perhaps
is to refer to the talk by Turiachi, where he considers them as one.
Oh, sorry. So you're thinking of so I'm only considering here the S3, so SD minus 1 topology. But something that we're trying to understand in light of Joaquin's talk is what happens when you look at the norm of, for example, the S2 cross S1 topology Hartle-Hawking state. So in particular, one thing you could do is you can write down what you think the answer is in terms of the Euclidean manifold, kind of like you could imagine in this case that the answer would be the sphere partition function. That's the level of the analysis that Joaquin and friends were doing. But I mean, you could try the analysis that I described here with that as well and see what you get.
Yeah, so I'm a little bit puzzled why when you include inflaton, you still have SOD, 1 invariance. Because naively somehow, yeah, once you include inflaton, just that symmetry is just broken very badly. Yeah.
So some aspect of this was actually, I learned this at least from some nice paper by Jeff about something about clocks are just a way to tell time, something like this. But the basic picture is that, so you're not fixing the value of the dilaton. You're actually integrating over all values of the dilaton. So it's related to the fact that the actual inflaton wave function looks like the Bunch-Davies wave function plus, which is SOD1 invariant, plus an additional linear term, which goes like the zero mode, for example, of the configuration infinity. In the zero mode itself, the 0,0 component is inert under SOD1. But I think that maybe the picture that you have in mind is a picture we fix the value of the dilaton. That's not what I'm doing. I want to integrate over the fluctuations of the dilaton because it's
But somehow you need to put a little bit a different boundary condition on the inflaton, other than not just treat it as ordinary scalar field. If you treat it as ordinary scalar field, of course that do anything. But somehow the fact that the universe somehow the inflation terminates, etc. Somehow.
Inflation terminating is exactly the right. Yeah. So you might imagine that if you want to glue this onto some flat space, you want to somehow figure out how to glue this onto a different patch of space-time corresponding to what happens when inflation terminates. I don't know how to deal with that, and indeed maybe this problem goes, that as you say, maybe that would kill this.
where it's just a linear potential. And so, V prime was order 1. So there's no end of inflation or beginning. Elton.
Hi, thanks for a nice talk, Jordan. So I wanted to ask about the resolution of the identity, because see, the inner product and covariance, I can think of covariance arising from a wave function with support only on geometries that have a non-compact isometry group. Like you do find a volume of a non-compact isometry group. And so for those cases, group averaging and standard group averaging diverges. And at least in finite dimensional cases, sometimes that requires renormalization. So since here you might have divergences from group averaging, but then you say the resolution of the identity is an inverse of this inner product, like does this pose any challenges to really formally describe this resolution of the identity? Did that make it vanish in certain parts or?
Well, my view of this is that, at least from the point of view of doing a path integral computation. So again, I didn't do it from the perspective of group averaging, but rather from the perspective of the path integral. From the path integral computation, this looks standard. I agree that from the group averaging interpretation, you have to deal with the fact, as you're saying, that there's this, basically, as you're saying, a different way of putting it is that the gamma prime inner product contains this volume of SOD1, and then when you do the resolution of the identity, it's the inverse of the inner product, so it shows up in the denominator. That is essentially what Held and Maxfield are saying. But at least from the perspective, whoops, I don't know what this is. At least from the perspective of the path integral computation, it seems clear what to do.
All right, in view of time, let's thank Jordan again.